Well, thanks very much in this. I'm looking forward to being part of this conference. I've learned a lot already. So there's so much to cover within this topic. We can't obviously do it all. So we'll try to focus a bit. And the framework I'll use is talk about local adaptation. That's generally at the field level. And I'll talk about tools, and we can actually talk about aggregate effects and global levels, but that's just a bridge too far. So there are some very interesting fundamental relationships that are emerging that I think can help us. One is a strong negative correlation between yield and risk. And so in favorable rain-fed systems with generally adequate and reliable rainfall, which in the U.S. would be the eastern edge of the Corn Belt, best example. Perhaps the most favorable agroecological zone in the world. In those environments, rainfall is reliable, soils are good, and yields are high and risk is low. In harsh environments, which would be the western part of that Corn Belt, because there's a rain shadow west to east due to the Rocky Mountains and the way low pressure systems move over the continent. In these areas, there's less rainfall, or soils are shallow and have low water holding capacity available to plants, so yields are low and risk is high. So if climate change makes rain-fed areas harsher, and I don't think it needs to change weather to do this, and Gene, we were talking about, it just needs to make it a little warmer, for instance, with the same rainfall would do the same thing, because evapotranspiration would increase with the same amount of rainfall. It would shift to a somewhat more harsh environment. So if climate change shifts agroecosystems in that direction, we're going to be moving on average from systems that will be somewhat lower yielding but much higher risk. I want to show you. So this is data from Iowa and Nebraska. So we're talking about the central part. I've got the center of the universe outlined here. But we're talking about the next state over would be Iowa here. And that's in the heart of the favorable zone of the Corn Belt. And we're talking about Nebraska here. So we're covering a very large rainfall gradient. And what we see, and that's interesting on this computer, how that happened. But those are temperature and those are up there, temperature and solar radiation. Is that right? Temperature and solar radiation that are black. Those are the patterns over the year for Ames, Iowa here, which you don't see, and Holdridge, Nebraska here. So the western edge of the Corn Belt, the central Corn Belt. But what I wanted to, this is, yeah, and the key here is the water deficit. So the temperature patterns, solar radiation patterns don't really differ here. What differs is the magnitude of the water deficit, which is the difference between evapotranspiration and rainfall. And in the western Corn Belt, it's about eightfold different, eightfold more intense. There, the numbers are 252 millimeters water deficit versus 32 in Ames, Iowa. And what happens then is across that, if we just plot county average yields over, I think it's a 5-year period, so a lot of observations, you see this incredible relationship between average yield, over 10 years, 2001 to 2010. So each one of those points is a county with 10 years of data, and you get a coefficient of variation and an average yield. And you see this very nice relationship. So these are irrigated maize in counties, mostly in Nebraska. You see very high average yields and very low coefficient of variation. I mean, 5% coefficient of variation. Favorable rain-fed in Iowa, and then the range across Nebraska. We say there's more climate change from the the western border of Nebraska to the eastern border of Nebraska than there is from the eastern border of Nebraska to the Atlantic Ocean. And you see the same pattern for soybean. And what's interesting is, and I want you to just quantitatively here, notice that if you're down at an average yield of 4 tons per hectare, we have some counties that do that in Nebraska, try to grow corn, you've got about 50% coefficient of variation. That's very high. Highly risky. You probably wouldn't grow it without crop insurance. What's interesting quantitatively is that we've been able in our global yield gap atlas, and encourage you to look at, where we actually have real data on cropping systems and soils and climate data, real climate data, long term, and we have it at these locations shown in those dots across a number of different climate zones and so forth. It turns out that you get a very similar relation. Now, this is simulated yield because in Africa they don't use fertilizer and they have no pest control. But these are simulated rain-fed yields where you have very little limitation due to nutrients and weeds, very similar to what we do in the U.S. And I want you to notice it's a different scale. But if you're at about 4 tons, you're at about 50% coefficient of variation. Yeah. It's a different scale, apologize. 4 tons, 50. 4 tons, 50. I think these are fairly generic relationships between yield and risk. What it is, it's the trade-offs that occur with temperature, rainfall, evapotranspiration, and soil depth even, and the effect it has on the crop. And I suspect these are fairly generic. And what it means is that if you are in these high-risk areas, though, you're going to be very concerned with dealing with harsh and uncertain environments. And so now, from that, I'd like to talk about some local adaptations. And the first is the importance of soil quality. And so what we're talking about here is a very quantitative relationship, really. And whereas I can't tell you exactly what I would measure for soil quality, we're talking about those attributes that confer yield without inputs. So higher indigenous soil nitrogen supply, greater water holding capacity, better rooting structure for deeper roots, etc. What it means is that for that quality, if you had a soil at an initial state, if you've reduced any of those inherent resource supplying or conserving properties for the same level of inputs, whether it be rainfall, energy, fertilizer, you get lower yield. And so you've got to make up for the decrease in quality with inputs. And anytime you have to manage inputs, there's always questions about margins for error. How much, when, what form. And so there's some additional risk associated with their use. And it contributes more than it's a inherently riskier system. And you can have soil degradation, of course, such serious nature that it actually decreases the seedling yield. And that would be a case of salinity or a hard pan form, roots can't go down, etc. But anyway, point is soil quality, maintaining soil quality is critical in dealing with harsh environments and uncertain climate and climate change. I want to talk then about other local adaptation, field level adaptations, tactical field level crop management options, and strategic investments. And of these, when we come to tactical, there are those that have extremely low barriers to adoption. Others that take a bit longer, and others that require substantial new expertise, new equipment, and even research and development, so much longer term. I'd like to give a few examples. So again, tactical options are the lowest fruit, and there are things like adjusting planting density, planting date, and crop maturity of the same crop. We'll go back to this figure that I can't quite figure out what happened. It's in the translation from my computer to this one. But again, these are this would be solar radiation pattern that comes in here over the growing season for, again, Ames, Iowa. Holdridge, Nebraska, harsh rain-fed, favorable rain-fed. And then this is the temperature over the growing season. Not a lot of difference between the two sites. The difference is in water relations here. And so what happens across the Corn Belt, what farmers do very well, is change sowing rate. They change seeding density. So again, this is longitude now, and this would be, these longitudes are correspond to like Ames, Iowa here, Nebraska, Colorado. It's all rain-fed maize. And then this is the water deficit, okay, during the season, during the cropping season. And this is plant population. Simply changing sowing rate using good seed, you get about 95% emergence if you don't flood out or something. And so it's very fast. And what this does is very simple. In uncertain, with less than adequate rainfall, if the plant, and with the rainfall distribution, can we see that here? Yes, you'll notice the rainfall is skewed to early in the season. So your highest rainfall months are, May, June, April, a little bit into July. Then it's dropping off. Highest here is June, July, then a rapid drop off in western Nebraska. What happens is if you use all your stored water early during vegetative growth, you create lots of leaf area, which has high transpiration. When water starts running out at the end of the season, the crop self-destructs, it burns up, and you get very little yield, even with the same amount of water. So if you reduce your planting rate to match the total season water supply, you'll have enough water stored in the soil profile for grain filling. And it's the water supply and the light and the temperature during grain filling that have the greatest impact on yields. Well, a lot of work been done on this. But the point is, farmers know it and respond quickly and immediately. And this again, is a generic response. It would occur for any crop. And indeed, if you simulate, because the beauty of our Global Yield Gap Atlas here, I encourage everyone to take a look. If you Google Global Yield Gap Atlas or simply www.yieldgap.org, we have all the underpinning data that allows you to do these kinds of analyses. And this is in Burkina Faso. And we have two sites. A site with low rainfall, Bugandi, and the average yield, this is simulated rain-fed yield potential of 5.4 tons per hectare. Not a lot of difference with Gaua, where there is a little more rainfall, but these are both harsh rain-fed environments. But what really differs, of course, at the two sites is that rainfall and rainfall distribution. In Bugandi, you're just at that critical threshold where if you use up too much of the water early in the season with high plant densities, your coefficient of variations skyrocket. This is, again, you're way up to 30% here. And you'll note you're still increasing long-term average yields. But farmers in these environments would be risk averse. So they plant with lower densities here, 31,000 plants per hectare here. And they try to maintain some consistency in yield. Farmers respond rapidly with planting dates. Again, whether it's large-scale mechanized, and by the way, these are scale independent, really. So small-scale farms, large-scale farms could low barrier to adoption. So farmers respond rapidly if they perceive climate change, or also with regard to improved technologies. The technologies are probably more important than the climate to date. The climate signal in the Midwest is not huge, but it's there, especially primarily in the spring months. So you can plant a little earlier. But what's really driven it is the fact that we have planting equipment now that gets perfect distribution of seed at very high speed. You can plant into stubble, so you can do no-till, conserve water. You get more disease, so you need to be protected against disease and insects, so you have seed treatment. And of course, varieties and cultivars that are insect and pest resistant. But you can see the steady progress, and I don't have the numbers for you off the top of my head, but for both maize and soybean, You're talking for maize, perhaps half a bushel a day, and for soybean, 0.2 to 0.5 bushel per day per year of increased yield simply by moving planting dates earlier. So these are things that can happen very quickly. They often need supporting technologies to be able to do them. I want to talk now about options that have longer term time frames, but not very long. So things like changes in tillage. I don't have data here to show. We have data. So in Nebraska, if you no-till, because you capture blowing snow, you save 25 to 75 millimeters of water. Snow doesn't blow off your field. The stubble captures it. It infiltrates. We get 20 kilograms of maize grain per millimeter of water. That's 0.5 to 1.5 tons per hectare simply from using no-till. We can also, in steeper land, construct conservation structures, the bunds across the hills. There used to be government programs that helped pay for this. I'm not sure if there still are. But it was very effective in reducing erosion, but also capturing water that would otherwise run off. Now, a number of options generally require new expertise or investment in equipment. I don't have equipment here listed, but new equipment. I think Robert mentioned that for new crops, for instance, and or investment in research and development, developing new crops, because it's chicken or egg. You've got to develop a crop for a market and a market for a crop. And since biblical times, humans have developed maybe 5 new major crops in 2,000 years. You can count on one hand the number of crops we've domesticated or developed new. But even switching crops, if you're in a traditional maize production area and you'd like to grow chickpea or faba bean, I mean, considerable research and marketing required to do that. We do see changes, though. So major changes. This is, again, in Nebraska and Kansas. So whereas in 1970 we were growing 2 million hectares of, this is hectares, 2 million hectares of sorghum. This is rain-fed, and much less rain-fed maize. In this time series of about 40 years, it's switched to now we're up at 2.2 million hectares of rain-fed maize and less than 1 million hectare of sorghum. Now, this is a fairly harsh rain-fed environment. These Kansas, Nebraska would be mostly considered the harsher side of the western side of the Corn Belt. What's happening here? Sorghum's more drought tolerant than maize. Well, it's the conservation tillage and the ability to store more water, and the fact that corn has a higher yield potential, just because it's inherently higher yield potential, the way the single ear, the annual crop versus a perennial crop for sorghum. So that in favorable years, so this is planting maize yield versus sorghum yield for all the counties in Kansas and Nebraska that grow both crops under rain-fed conditions. So what you see, farmers' response here is quite rational, because it's only at very low yield levels, meaning bad years, either a county way out west with low rainfall, or a year in a more eastern county that was very droughty. And even though this is a 15 to 20% yield advantage of sorghum over maize in those years, it's a 15 to 20% on a very small yield. And so in contrast, as years get better or in counties with more average rainfall, the advantage switches quickly to maize. And even though this too is about a 10 to 15% advantage of maize to sorghum in favorable environments, it's 15 to 20% on a much higher yield level. And so farmers choose to grow maize, and maize has displaced sorghum. And again, no-till has helped here. So you can switch, farmers do it. You can even switch cropping systems. So not only, so in that system it might be sorghum, soybean or maize, soybean. Now we can also think of introducing other crops as well. And again, I think it takes a bit longer, but farmers are very good at this. So this is what's happened in the U.S. Corn Belt. This is all the states of the U.S. Corn Belt in 40 years or so of the Green Revolution. What you can see is that in the beginning of the Green Revolution, farmers were quite diversified. And they grew not only corn and soybean, but they grew significant amounts of wheat, alfalfa, oats, and barley. But by 2006, 2008, I mean, these systems are just about all maize and soybean. But the point is, farmers are very good. If there's reason, farmers can change their entire cropping system and bring in new crops from among existing crops. I think the fundamental question we have, though, that's worthy of prioritized science is how much diversity is enough to ensure sustainable staple crop production systems with changing climate. Because we often hear, diversity is stability, that our systems are far too dependent on just a few crops, et cetera, et cetera. And the science supporting that is not so clear in agriculture. For instance, continuous irrigated rice in Asia, double and triple crop each year for 40 years, have proven quite stable under irrigated conditions. So, but the point here is it's still an issue, and it's a very important one. But what I want to say is your flexibility in considering how to diversify a cropping system or alternative cropping systems, whether it's in response to economics or in response to climate, it depends on what type of climate you're in. So the most flexibility, of course, are in warm, humid, tropical environments with good soils, deep, well-structured, high water holding capacity. Good example would be the Cerrado of Brazil. Those systems could grow anything. They're growing mostly soybean now. You could grow almost anything there. They need fertilizer, they need lime, but they're very good soils once you take care of the nutrients. You're constrained a bit more if you move from the tropics to the temperate, and that's because you get a period of cold. But examples here would be the Argentine Pampas and the Balkans. Typically those farmers right now have access to 5 or 6 good major staple crops, and they can move them around and change. Once you get to cooler climates still, cooler temperate, that would be Northern Europe, North Central USA, you start becoming limited by your growing degree days, even though you have a lot of water. And so in these areas, you're limited because not all crops can grow under these cooler temperatures. But you've got great soils and great water. And then, of course, you're most limited in your ability to think about adjusting your rotation in response to climate or economics if you're in warm climates with less water or poor soils. And I think there's some issue about where perennials fit in. I see a lot of interest in perennial grains. I see funding going there as well. My concern here is that I think where perennials would do better than annuals are areas that probably shouldn't be farmed, but that's to be seen. Finally, I want to talk about options that require substantial new expertise or investment. And the best example is irrigation. And, people have known about irrigation a long time. And as I showed you earlier, it's because if you're a society, and what societies have done is allow specialization, so you can raise armies and have a wonderful culture and arts, allows people to specialize and support them outside of agriculture. It's because it gives such high, stable yields. I can't tell you what it means to know what your yield level is going to be if you want to manage nitrogen efficiently. When you don't know what your yield is going to be, it's so hard to manage nitrogen and contain it in the root zone. And so globally, we've found this out as well, and now approximately 18% of total crop area accounts for 40% of total food production. It looks like we're having trouble finding new areas, and existing areas are running out, and this is a problem. So I would like to put this on the table, and it follows for what Robert said. And that is, and I don't hear it discussed as a key component of adaptation to climate change. So number one, we've got to maintain integrity of reservoirs, existing reservoirs and conveyance structures. We've got to have informed, effective, and efficient policies, regulations, and institutions to avoid overdrafting and avoid negative environmental impacts of irrigated agriculture. And we need to have, and this is additional, we need to have active, proactive, public and private sector is doing okay, but public sector investment in research, development, and human resources to improve efficiency and advance irrigation technologies and equipment for both small and large farms and farming systems. And this, I think, has to raise, if you were to truly value the impact in a quantitative way, the way good economists could, this would have to come way up. And I think for Africa, it becomes very important. A recent paper we published on the topic. And indeed, Africa is very fortunate. And by the way, currently only 5% of Africa land, arable land, is irrigated, compared to 33%, for instance, in Asia. And so, fortunately, there are lots of water resources. This is even obsolete because many of you have probably heard they've discovered large fossil groundwater resources in northern Kenya. But the point is there's enough water to expand irrigated agriculture substantially using rechargeable, sustainable aquifers and surface waterways. And there are ways to look at quantitatively how to prioritize where to do that. And what you want, again, would be systems for which rain-fed agriculture, so this again is our data from our yield gap atlas, rain-fed agriculture has very high coefficients of variation. These are different soil depths. This for a different purpose. This is looking at one of the things we have very poor data on effective root zone for soils in sub-Saharan Africa. So it's kind of a guessing game attributing a soil depth, which determines how much water you can store for rain-fed agriculture, regardless of what your rainfall is. But assuming different soil depths, so you can see it across the range, some areas would benefit a lot more because their rain-fed agriculture is so variable. Year-to-year variation. Coefficient of variation here is the degree of annual variation in yield. So it's the risk. And so you could choose certain areas and certain systems where if you had groundwater resources, these would have perhaps the best social benefits. Some tools I'd like to end with that are essential are public access to weather data, has to be good quality, long-term daily time step, and of course continuous improvement in crop genetics, particularly in crop stress tolerance. There's others that will talk about that. My only point here is there's no silver bullets. It'll be small, incremental, but we need it, and it's critical. I want to talk about weather data and end. Obviously, if you're concerned about climate change, one of the things that that farmers need is access to good quality, daily time step weather data and historical records so they can use the historical records to look at probability distributions of outcomes against real data during the season that's always updated as the season comes along, and you complete the simulation of the season with the historical weather data, and you can look at probabilities for yield for a given field in a given year, and then make management decisions accordingly with fertilizer. Cost of water, I'm going to cut an irrigation here, whatnot. But if you're going to respond to climate change, there is nothing more important than getting access to weather data. Well, here's where the bad news is. For one thing, there's a lot of people that realize the value of weather data now in the private sector. And it takes public sector money to maintain a good, robust, publicly available weather system. And there's been terrible disruption to the funding of those systems with recent budget problems at the state level. No one wants to fund something. Why do we need that when we have weather station at the airport? Well, the reason is the NOAA system is all at airports or in cities now. It may have been in a more natural setting when the NOAA station was established 20, 30, 50 years ago, 100 years ago, but now it's been covered up by cities or they've just put it in an airport. These are much warmer than in rural areas. So we can't use the weather data from Lincoln, Nebraska at the two stations because they're often, on average, 1.5 to 2 degrees warmer than in farmland that's just 10 kilometers away. And I think it's very good if the private sector wants to make a profit on using publicly available good quality weather data for agriculture. That's what I hope Monsanto is going to do. But not if they encourage the government to walk away from funding a good public network of weather data so that they're not only providing how to use it, but the weather data themselves. And this is why. So it gets back to the question I asked of Robert. And that was the importance of real weather data. So all of the studies that have looked at using crop models to simulate impacts of climate change on crop yields have used gridded weather data of some sort. You have CREW, I think this is CREW, you have an NCEP database, you have a NASA power database. So we can take those data and simulate crop yields with those data looking back 50 years or 30 years versus simulated yield with a control weather database in the grid. And these are flat areas, so there's not a lot of spatial geography that varies. And you see the correlation's very poor. So if you use gridded weather data, the basis of most of our studies on impact of climate change on crop yields, they don't predict crop yields well. They don't predict the mean, and they don't predict, and they have tremendous bias. This is another way to do it that uses available weather data I won't go into, but it's real data on real data, NOAA weather observed in areas that are not airports or cities. And this is for rain-fed maize. So there's a real need for having big data, particularly weather data, actual data, not gridded data, for predicting impact on climate change. So here's bottom line for weather. Here's maize distribution in the Corn Belt and High Plains. Here's the NOAA weather stations. Oh, NOAA and Mesonet. Now, Mesonet is a system that came up later after NOAA, and in some cases can use a NOAA station, but mostly not, that was developed for agriculture and specifically located in an agricultural area away from influence of cities. Now, when you take out the NOAA stations under the influence of urban or an airport, you're left, so here you're up to 2,800 stations. You're now down to 747 stations, but of these, because of the attrition, because of the reduction of funding, and only 316 stations have what I would call good enough data to be able to use historic data in a yield forecasting way for the current year. And this is a travesty. And so what's happened in that response? You're now seeing private sector coming in to provide simulated black box weather data and selling it to farmers. The tragedy is it's, of course, even worse in developing countries. So here's a map of what I would consider to be weather stations of adequate quality to be able to have any degree of certainty about simulated historical yields or used for real current time data. So in a world threatened by climate change, I find it ironic that we're really lacking in climate data and no apparent public commitment to maintain it or develop it. And this has to be, for the amount of money it would cost and its benefit, has to be one of the highest priorities. Yeah, so the big picture I want to end with. I think nearly all future climates, maybe not the 4-degree model, but nearly all future climates with potential to produce food exist somewhere in the world today. They may not be in the same place, but they exist. So learning how farmers currently deal with today's harsh and variable climates provide important insight and understanding on how to mitigate risk, and we haven't even talked about the need to double yields on existing farmland as a key strategy for climate change mitigation. But part of that is you've got to continue to raise yields, got to mitigate risk in the face of climate change. And there's so much to be learned from what farmers have done and are doing. And so, yeah, what we need is more investment in research and development in those areas. And finally, just much of what I've talked about is in a textbook that I would like to ruthlessly inform you about that I think has some of the basic principles here that can help us deal with climate change. So thank you very much.